welcome to the second RIKEN AIP IIT Hyderabad joint workshop. So my name is Masashi Sugiyama. I'm from RIKEN AIP. So good morning in India and good afternoon in Japan. So we are connected online. So here's the workshop program, 2 days. So we have a lot of great talks. So after introduction of RIKEN AIP and IIT Hyderabad, we have many talks today. And then after a short break, we have spotlight talk. And then at the end, we have another session of talks. Then each talk should be something like 19 minutes, and we have 5 minutes question and answering. For spotlight talks, we only have 5 minutes and no question and answering. We have 2 days, and hopefully, so we have a lot of good talks and good discussions, and we hope to find good opportunities for collaboration. Okay, so please enjoy the workshop. So then I would like to immediately go to the next part, so opening by VIP. So let me briefly introduce RIKEN AIP. So I'm director of the center, Sugiyama. RIKEN founded the Center for Advanced Intelligence project in 2016, 10 years ago. We have about 140 employed researchers, and more than 40% are international researchers, and about one quarter are female researchers. So we are quite diverse. And we have more than 300 visiting researchers from universities and industries, and we have more than 100 domestic students as part-time researchers. Then, so we are accepting international interns, and in total, we accepted already 228 interns so far. So our central office is located in the center of Tokyo, and we have a nice room like this, distributed across different universities. So that's why our offices are distributed across the entire Japan like this. Then, okay, in RIKEN AIP now, so we have 3 research groups. So they are called Generic Technology Research Group, Goal-Oriented Technology Research Group, and AI in Society Research Group. And each of us are working on like learning and inference algorithm, statistical and optimization theory, or AI for science, AI for societal problems, and also personal data management, security, economy management, ethics and governance, so things like that. So we have quite diverse topics covered by AIP. Then the Generic Technology Research Group developed new AI machine learning technology. And I don't really go into the detail, but we have like machine learning theory and algorithm for foundation models, sequential decision making, and also optimization, multi-level optimization. Then the goal-oriented technology research group worked on accelerating scientific research, like antiplate crustal deformation analysis. So earthquake research is quite important in Japan. Or so data-driven science. So we try to extend the statistical test to more data-driven manner. Well, we have nice clinical application of ultrasound diagnosis support. And also we are working on global 3D land cover mapping. It's an important challenging topic in the community. Then the AI in Society Research Group worked on AI ethical guidelines or personal data management, security, and reliability. These are quite important topics, and we are discussing these topics all together. So then this highlight, so machine learning conferences are quite important for our field. So we submitted papers to NeurIPS, ICML, ICLEAR, AI Stats, and the number of papers are growing in this way like this. And in addition, so we have many general chairs, program chairs, and also plenary talks and keynote talks. So MT, congratulations. So he is a program chair for AI Stats last year and general chair for this year. And Taiji is a plenary speaker this year at AI Stats. So these are great things. Then we have a lot of international collaboration partners. Then, so IIT Hyderabad is, of course, one of our important partners and listed here. We are quite happy to have a workshop today and tomorrow. Then, so more specifically, so we had already a lot of communications between 2 institutes. So, like, we accepted the visit by IIT Hyderabad already twice by their directors. So, once in 2018 and once just last month. So, we had very nice communication with the directors. Then so we already had an MOU and it was also renewed, and now the current one is valid until the end of March 2027. We have 1 more year. So hopefully we can discuss more collaboration opportunities and maybe exchange lab, and hopefully we can extend our MOU again for further collaboration. Then we had a joint workshop in Hyderabad in 2019. Then this time, so we decided to have an online workshop. Hopefully, we want to bring IIT Hyderabad people to Tokyo and have a in-person workshop in Tokyo. But maybe next time. So this time, let's focus on the online workshop. Then another thing is the Asian Conference on Machine Learning. So this is something. So I was the co-founder. We started the conference in 2009, so 17 years ago. Then we organized SML in Hyderabad in 2022, so right after COVID. So it was a bit challenging time, but the conference was so successful. So Vineeth was the general chair, MT was the program chair, and also many IIT Hyderabad faculties served as organizing committees. So the conference was quite successful. And hopefully we can also have another like international conference or some interesting event in Hyderabad in the future. Then, so AIP is actually changing. So we are on the 10th year, and the first AIP project actually finishes in this month because we complete the 10-year project. And from this April, we will have the kind of second AIP project, and we have new research organizations. So new three groups are named as mathematical intelligence, domain intelligence, and physical intelligence. So mathematical intelligence try to elucidate the fundamental principles of cutting-edge AI and also creation of the new concept for high reliability AI. Then the domain intelligence group try to develop AI technology specialized for domains such as science and industry. Then physical intelligence group try to develop AI technology adapted to diverse data from the physical world. So these three groups will be collaborating together to really advance AI technologies for the future. Okay, great. That's the introduction of RIKEN AIP. So now I would like to welcome Ganesh and Vineeth for introducing AI at IIT Hyderabad.
Thank you, Masashi, and good morning to everyone joining from India, and good afternoon to everyone joining from Japan. Uh, it's uh, it's a pleasure and privilege to have this workshop together with RIKEN AIP. As Masashi mentioned, we had the first edition of this workshop 7 years ago. Hopefully, the next one won't take that long. It was in 2019, and apart from many other things, as Masashi pointed out, one of the significant outcomes of that workshop was actually organizing ACML, which did have a good impact in Indian machine learning ecosystem in general. Hopefully, this workshop will also lead to such tangible outcomes that come out of discussions. This is apart from student visits and faculty visits and collaborations that also happened out of the visit. The other thing I wanted to mention is that the first edition of this workshop happened in 2019, and one of the significant other correlational outcomes that also came out was that IIT Hyderabad started the first AI department in the country in 2019. So, in fact, the first AI department in India was at IIT Hyderabad, started in uh, April 2019, just after the workshop. And IIT Hyderabad also started the first bachelor's program in AI at that point. So hopefully, if not directly, in at least in an indirect way, this workshop will also lead to some significant outcomes that come out at IIT Hyderabad too. So with that brief note, I'll just hand it over to the current head of the AI department, Dr. Ganesh Ghalme, to give a brief introduction of the AI department. Over to you, Ganesh.
Thank you, Professor Masashi and Vineeth, for putting together this workshop. And also, after a long time, hopefully, we have many more engagements soon. I'll now present AI department at IIT Hyderabad. Professor Vineeth, as Professor Vineeth said, we started our AI department in 2019, the first in the country, at least among the IITs. And we have we started this program with students, from every both undergraduate as well as postgraduate degrees at the same time. Um, so yeah, we started with the understanding that we need to train students, also have collaborations and research in several dimensions. This includes AI theory and applications and practice. Um, right. So 2019, we have grown from 20 BTech seats and a few master's seats, around 15, to a 50 seats per year in our BTech program, that is undergraduate program, and similar number in our master's program. So we have grown in terms of size. We have also grown in terms of our capacity, in terms of research areas, collaborations, and so on. So this is a brief timeline. We have conducted several, as Professor Masashi was mentioning, ACML, and also Weibo Summit in 2020. Several such initiatives we have introduced now. Very recently, we have introduced several courses, including AI in finance, AI in cybersecurity, AI in healthcare, and so on. We have started with a couple of centers, including Aishwaryam Center for Sustainable Development. This is in 2024. And we have been growing our collaborations with industry partners, with the government organizations, with international academic institutions, and also the corporates. So in terms of numbers, we have a 28 faculty member group, out of which 6 faculty members are core faculties in the AI department, and rest 22 are affiliated to the AI department from other departments. So this includes Professor Vineeth from Computer Science Department, Professor Srijit from Computer Science Department. So many faculty members from computer science, electrical engineering, mathematics, as well as mechanical engineering, chemical engineering are affiliated with the AI department. The current strength as it stands, I think this is from 2015. I'm sorry for presenting the old data, but the current strength is around 250 students, and many publications at several top venues, including ICML, AAAI, HKIs, NeurIPS, CVPR, and so on. And this is the distribution, almost equal split between undergraduates and postgraduate. 137 undergraduate students and similar number in for our postgraduate programs. So just to give a very brief, in terms of the students we get and the quality, maybe the performance of the students in the entrance exam, the closing and opening ranks of the AI department have been consistently around 600 to 800, which in an entrance exam for, so JEE stands for those who are from Japan. JEE stands for Joint Entrance Exam. This is a centralized exam for undergraduate students to be admitted in IITs. And this is very competitive exam, and we're doing reasonably well. We're doing very well in terms of attracting top quality students. GATE is its counterpart for the postgraduate admissions, and we're doing reasonably well there too. Right. So in terms of publications, we are publishing consistently in several top venues. This includes, again, as I mentioned earlier, the CVPR, ICML, NeurIPS, HKI, and so on. And also several journals, top quality journals, including TMLR, DMKD, and so on. Main areas of research include AI, foundational AI, that is statistics, online learning, statistical learning theory, machine learning, as well as deep learning, computer vision, natural language processing, and many applied areas, including robotics, AI in healthcare, AI in sustainable cities, and so on, sustainable development, and so on. Yeah, so this is basically the list of what we work on, and we collaborate. We're open to collaborate with industry partners, with educational institutes on projects that are, of diverse nature, including research projects, including development projects, product development and so on. In terms of applied and interdisciplinary applications, we do have faculty members that work in manufacturing, in healthcare domains, in cybersecurity, robotics, and transport, and we collaborate with them, add value by introducing the AI components in these applications, and writing joint proposals together, guiding PhD students or master students together with them. Yeah, and these are some of the short highlights, or maybe this areas of strength. AI department in particular, but in IIT Hyderabad in general. So healthcare, sustainable development, responsible AI. I've not put a lot of them, but robotics is another area where we do have some strength. And yeah, so that's I think that's a short introduction of the AI department. I would like to take this to Vineeth. Thank you.
Yeah, so thank you very much, Ganesh and Vineeth, for the very nice introduction, and congratulations for the great success launch of the new AI department. So it's clear that topics are quite overlapped between
Yeah,
two organizations, so we should be able to find a lot of common topics so through this workshop. So thank you very much.
thank you.
I will introduce our recent work. My name is Takayuki Osa. I'm the team director of the robot learning team. So my team is actually quite new, so it was established 1 year ago. So I will just showcase our recent work. So as many of us know, many people are working on robot foundation models now. So robot foundation models are typically trained based on the vision language models. Then here I will call it vision language action models, VLA. VLA models enables robot control through natural language, and it also makes robot accessible to everyone because we can control the robot without expert knowledge. So this is a fantastic part of the VLA models. Behind the emergence of the VLA models, there are two factors. So one is the model itself scaled up significantly. So typically, these VLA models have billions of parameters, like 7 billion or something like that. And also the size of the dataset also scaled up. So in this project called Open Cross Embodiment Collaboration, so we collaborated with international researchers all over the world, and we collected nearly 1 million robot trajectories, and we built a single dataset. So we require this kind of large-scale dataset for training large-scale VLA models. And here we can see the pipeline for training large-scale models. So as I said, we need massive data for training large-scale robot models. So we first collect the data, then we perform the supervised learning typically. So we collect the data for multiple tasks and the data from the multiple cross embodiments. Then after we train the model, we deploy the model into the real world. So it's very simple, but how we need the scale of the both models and dataset. So this is very nice, but so there are some obvious limitations of this current framework. So one is the current performance is still limited to simple manipulations. So here you can see the performance of the model. So if we input the language instruction like move apple on cloth, then the robot will pick up an apple and then move it to the yellow cloth. And we can see the something similar on the right-hand side as well. But still, we just have a two-finger gripper and also a single arm. And also, the performance of the single-shot performance is very limited. For example, if you bring your model to the unseen environment, the performance is not very good. So typically, you'd need to correct additional demonstrations and fine-tune the model. based on supervised learning. But actually, the various models are often depending on the supervised learning. So this means that we need a large amount of demonstration. Then this is actually time consuming and costly. And also, so as I said that we collected nearly 1 million robot trajectories for training this kind of simple models. However, if you want even more complex tasks with, for example, with bimanual system with a multi-fingered hand, then that would require even more data. So actually, this is almost infeasible for a single laboratory. And also, we also need heuristics for data collection. So typically, so it is often said that a single demonstrator should perform the skill consistently. That otherwise, this distribution of the action is multimodal, and then the performance of the model may not be good. So these are the limitations. So far we have identified how powerful the robot foundation model is, but actually the supervised learning, so which is used for the current framework, is not enough for training BREAD models. Then also we need to we already know that training with a pre-corrected dataset is not enough for zero-shot adaptation. So these are the limitations. So again, we come back to this pipeline. So there are challenges in the robot learning. So the first question is how to collect samples. And the second question is how to train the models, how to capture diverse behaviors. Then also the third question is how to deal with the distribution shift in the real world. So I will introduce some of our recent work that addresses these challenges. Okay, then I will first talk about how to train the model. Then, so before I go into the details, I want to clarify the problem settings of the reinforcement learning. So I just talk about reinforcement learning in this presentation. So in reinforcement learning, we assume the Markov decision process. The environment should follow the Markov decision process. So we have the environment, and we have the state, and then we also observe the reward. So if the agent takes the action following policy pi, then we will transition to the next state and reward. So the objective is to maximize the return, which is the sum of the discounted reward. And also, I would like to clarify the two data collection regime in reinforcement learning. So one is online reinforcement learning, and the other is offline reinforcement learning. In online reinforcement learning, so we iterate data collection and training of the policy. So this is kind of traditional and popular and common framework for reinforcement learning. And the other framework is offline reinforcement learning, where we just use a pre-corrected dataset. Then we correct the dataset and train the policy and deploy it directly. So that's it. So this setting is a bit different from the online reinforcement learning, but this is actually suitable for training a large-scale dataset. So in this kind of the large-scale dataset, we have nearly 1 million trajectories. Then we want to exploit such large-scale dataset as much as possible. So this offline reinforcement learning addresses these challenges. So then here, now I'm interested in discovering diverse solutions in offline reinforcement learning. So to motivate this research, I'd like to describe the difference between the human adults and kids. Human adults can adapt to the new environment and can learn a new task very quickly. However, the human kids cannot do that as human adults do. So what is the difference between adults and kids? So one aspect is a skill library. So human adults usually have the experience of this performing the diverse tasks, and then they have a kind of the library of performing the diverse behaviors. Then such kind of skill library is useful for few-shot adaptation to new tasks. So to achieve the adaptive behavior of the robot, probably discovering the diverse behaviors is very beneficial. So if you could develop skill libraries autonomously, then we can make the robot more adaptive. So based on this motivation, we worked on an algorithm that finds multiple solutions in reinforcement learning. So actually, it is known that there can be multiple optimal policies in reinforcement learning. So if you think about agents that work at a certain speed, there could be multiple walking style like this, for example, hopping or one-leg hopping or two-leg walking or something like that. Then if you could have diverse walking behaviors, probably we can adapt to a new embodiment, or even if the robot gets broken or something like that. Yeah. Then, so to model the diverse behaviors, usually this kind of latent condition policy is used. So here, this is a definition of the typical policies, which is a conditional distribution of action given state. Then we now decompose this policy as this. Then here we have a latent condition policy, which shows the different behaviors with different values of the latent variable. And then here, this P of Z is the prior distribution. Then typically, we use a uniform distribution so that we can have diverse behaviors. Then for training this policy, we typically use this kind of objective functions, which is given by the sum of the task-related real term and the diversity term. So by maximizing this term, so we can ensure that the behavior is useful enough. Then by maximizing the diversity term, we want to have as diverse behaviors as possible. So typically, the diversity term is quantified as a mutual information term, and this task-related real term is often formatted as a latent conditioned Q function term. Then, so in our recent work, we developed an algorithm that finds the diverse skills unsupervised manner. So here we developed an algorithm that iteratively learn the skill latent space, and policy that is conditioned on the latent variables. So here is a result. So for example, here we have trajectories from starting from blue points to the red point. Then our method can find diverse ways to approach the goal points like this. And here you can see how the latent space is spanned in the state action space. And also here is the result of learning the diverse behaviors from the offline dataset. So here we can see that how diverse behaviors can be obtained by changing the value of the latent variable. So here you can see the different behaviors of the hopping. So if you change the latent variable in this direction, the angle of the disjoint is changed continuously. And also if you change the latent variable in this direction, the angle of disjoint is changed. And if we learn this kind of diverse behaviors, we can quickly adapt to the different embodiments. So here, the blue link is shown as a difference between the embodiments. So we have the longer link for this blue link. Then even if the embodiment is different, we can quickly adapt to the new embodiment just by picking up already learned behaviors. Okay. So this is how we our recent work on how to learn the diverse behaviors from the offline dataset. Okay. Then we also have another work that address how to leverage offline data. And in our recent work, we address the offline cross-embodiment reinforcement learning. So in a typical offline reinforcement learning, we usually have the dataset collected from the single robots. However, we investigated how to perform the offline reinforcement learning effectively with the cross-embodiment dataset. So we developed a dataset that includes data from diverse robots, like this kind of quadruped robot or humanoid robot or this kind of ant robot. Then we investigated what happens and how to effectively perform the cross-embodiment of offline reinforcement learning. And in this work, we use the kind of special network architecture so that we can deal with variational state action space. So this network can deal with variable length inputs and outputs. Then we can control the various robots using this single network. Then interestingly, when we perform the cross-embodiment offline reinforcement learning, we observed both positive and negative transfers. So here in this blue sign, blue colors indicates the positive transfers. So we have the positive transfers between these robots. So these robots are very similar. Then on the other hand, we have the negative effects on these robots. So here in this data set, we have many quadrupeds robots, but less humanoid robots. Then these robots have negative effects from the other embodiments. So actually, the negative effects could appear if you perform the cross-embodiment of offline reinforcement learning. Then to mitigate this issue, we investigate the gradient conflict between the embodiments. Then, so here is the visualization of the distance between the embodiments. Then, and also this is a gradient conflicts between the different embodiments. So actually, you can see the similarity between these figures. So this similarity indicates the distance based on the embodiments is correlated with the gradient conflicts between the embodiments. So to mitigate this issue, we performed a group-wise update based on the embodiment similarity. So we made a group based on the embodiment distance. Then we performed the policy update based on the group. So this kind of suppressed the gradient conflict, and we could achieve the better performance in offline reinforcement learning. So I believe that this is a kind of the first step to perform the cross-embodiment offline reinforcement learning effectively, and then we will further investigate this direction for more diverse tasks. So in this paper, we just investigated locomotion task, but we will investigate a manipulation task or more diverse tasks in future. Okay. Then we also interested in the online reinforcement learning setting. In online reinforcement learning settings, so typically we use GPU-based parallel environments recently. So here you can see the massively parallel environments, so based on the Isaac gene. Then so here typically we can have thousands of the environments. So in this kind of setting, the PPO is one of the well-known methods for updating the policy, but actually PPO, it is known that PPO may not be very effective for some tasks. So actually the distributing the same policy for all of the environment is not very efficient. Then, so in this paper, we investigate a framework called leader follower framework. Here in this setting, we have the leader agent, which is a kind of the main policy which we want to optimize. Then also we have the follower policies that is very similar to the leader, but different, slightly different policies that will try to explore the state action space. Then we investigated how we should control the distance between the leader policy and the follower policy. Then we investigated how to achieve the effective or efficient state action space exploration. And in this work, so we successfully developed an algorithm that performed the exploration. Then our algorithm showed good performance across the different tasks. So this work will be presented in iClear this year. So if you're interested, please check it out. Okay. Then as a last challenge, I would like to talk about how we should deal with the distribution shift between the training domain and the test domain. So in our previous studies, we investigated vision-based offline reinforcement learning. So here, the input to the policy is the vision of the agent, like image of the agent, like this. Then there could be we aim to develop a policy that is robust against the change of the background, like this. So in the training domain, we have the background like this, but we want to obtain an agent that works with a different background as shown in this figure. So here we leveraged adversarial training framework. So here we introduce discriminator that tells the difference between the background. Then we try to obtain the visual feature extractor that is invariant in these domains. So using this technique that we could obtain the robust policies, then we developed good offline reinforcement learning algorithms. So we applied this framework for the real robot environment as well. So in imitation learning, so we obtained a data set from the imitations. Then we trained a feature extractor, which is robust against the change of the background or lightning condition or changing of the position of the obstacles or something. And so here you can see the video of the trained agent. So here, so we have the demonstration only from this environment, but we tested the policy in the different lightning conditions or different background, or we tested the environment with additional obstacles like this. But our policy works well for this kind of change of the visual distractions. Okay. Well, so far we are working on the algorithmic perspective of the robot, but also our work were usually based on small scale models. But we are planning to extend our algorithm for the more large scale models and more diverse tasks. So we will further explore the algorithms in future. So please stay tuned for our update. So thank you for listening.
Okay, thank you very much for the nice talk. Are there any questions? Yes. No, this is a clap. So let me start. So I'm interested in domain adaptation, the last part. So
Yes.
it looks like you are considering a covariate shift. Is it correct?
Yes, something like that. Yes.
But can you really address this kind of problem only by covariate shift?
Well, that's the question. So here, we try to obtain the robust feature extractor just by performing the data augmentation. And then by applying the data augmentation, we virtually try to generate domains fit might appear in the test domains, but we actually don't have any information for the test environment. So that's kind of the assumption we made. So that this kind of data augmentation should somehow include the test environment. So that might not be realistic sometimes. So we need to think about actually so if we could have access to some data in the real test domains, probably we can enhance the performance even more. But we need to think about how to do that in practice. Actually.
Right. Thank you. So then, Vineeth?
Okay, thank you, Takayuki, for the great talk. A couple of questions, slightly broad ones. One is obviously today the trend is towards using VLA models and foundation models for largely around robotic manipulation tasks. I wanted to get your thoughts on how generalizable are these to web agentic kind of frameworks. What I mean by that is, can we use similar approaches to, say, do action spaces to browse on a computer, like computer use agents or mobile use agents, things like that? Do you also see the same kind of frameworks being useful for other kind of action spaces? Currently, the action spaces are largely physical in what you've been doing. I'm just trying to understand how well this translates to other spaces. The second question is also about, because you've also been looking at foundation models, how important are reasoning traces for such domains? Right. So one of the primary work in foundation models is around reasoning traces in general. I'm curious to understand how important is that to this domain also.
Yeah, thank you for the question. So actually, probably you are interested in something like a web agent that performs autonomous tasks or something, right?
Correct. Because I see the difference as only the action spaces.
Yes.
So I'm just curious to see how it.
So I think we can actually apply the similar framework for web agent as well. So it's, as you said, the difference is just action space, the definition of the action space. So probably the kind of the technical difference is probably the for web agent, the action space might be the discrete, usually. For example, clicking some of the tab or link or something. And but yeah, basically the algorithmically the same. So probably what I would expect is that in future, so in the very far future, probably the single agent could deal with both the physical environment and the web agent. That could be possible. So, but yeah, so I'm not sure about it though. But
Okay, thank
yeah,
you.
then that's as the second part, the reasoning is actually the very important topic for physical robots as well. So in the current framework, usually the VLM models just address the very short horizon task, like the picking up the object and opening the door or something like that. But to solve the long horizon problem, so we need to probably decompose the big problem into subtasks, and then we need to think about how to perform the task sequentially. Then for that planning, we definitely need a reasoning module. Then, so actually the recent framework proposed by some of the startups actually employs a hierarchical framework where the very big where the models perform the reasoning to decompose task into the short horizon task, then the where models solves the short horizon behaviors.
Thank you. Thank you. Got it.
Yeah,
Thank you.
thank you very much. Thank you for the question.
One more question in the chat window. So thank you for the nice talk. I had a question. So what is the kind of geometry that is employed for the latent to derive multiple solutions in offline RL?
Okay, so here the geometry is just I would say simple standard Euclidean space. So actually we could use a hyperbolic space as well. I tried that, but it was not very stable in my implementation. But actually investigating the another geometry is a promising research direction, I believe.
Okay, great. So Takayuki, thanks for the nice talk.
Thank you very much.
Yeah, so today I will talk about learning in the presence of strategic agents, or otherwise called strategic learning. This is a kind of an approach where we do not look at the machine learning or AI models as if they're making decisions for the individuals, and these decisions are kind of or the data that is available for the decisions is a non-strategic one. So a traditional decision-making algorithm, machine learning systems, just take the data and gives us some outcome or some decisions. Think of these machine learning models being implemented in, let's say, banking or maybe loan decisions and so on in banking domain, where a classical machine learning algorithm just takes in historical loans data, features from individuals, and to make a decision about whether a person should get a loan or not, or maybe whether a person should be admitted for college or not, or similarly whether should person get a health insurance, and what should be the premium and things like that. Here human is involved. So this is another example. Here human is involved in individuals are involved in first providing the data, and also when these models are implemented in practice, the humans can manipulate their features in order to obtain desirable outcomes. So now agents have different goals and different information and also different actions available to them, which traditionally is not the traditional machine learning algorithms or traditional frameworks ignore. That is, we will consider throughout this talk and in this area in general, it is considered that the agents are rational. So given their goals, agents will take an action that basically best achieves that goal, given their information as well. What makes this area of research more interesting is that there is a misalignment in the objectives of the agents as well as the objective of the system, maybe the system developer or mechanism designer who wants to achieve, let's say, efficiency, whereas the objectives of individual agents are more individualistic. And that is, each individual wants a positive outcome, whereas the system wants the maximum accuracy as much as possible. Okay, so now I have basically compared it already, but let us look at let's go into slightly more details. So at the deployment time, let's say we have some model F or some classifier F. We assume in classical setting, we assume that the test data is drawn from the same distribution as the training data. That is, the deployment time, we do not see different distribution. However, in strategic setting, when we deploy a classifier, let's say F or model F, the features at the deployment time or at the test time are manipulated, or these features are kind of moved from their original position. So these features are not the same, or this distribution from which these features are coming are not the same as the distribution which F is trained on. And this introduces errors, right? So we call it a gaming if y prime. So that is when we have the feature xy and a modified feature or manipulated feature as x prime, y prime. So feature and label tuple. When the modified labels are same as the original labels, this is a manipulation or a gaming. Whereas when we see some improvement in the labels, or maybe improvement in the qualifications in these applications that we have discussed, this is called as performative prediction, just to set up the nomenclature. All right. So as I discussed earlier, so agents have one favorable outcome, and agents are rational. So agents will do anything in their power to basically get the favorable outcome. So we will say agents get 1 if they're classified positively. That's a favorable outcome, and 0 otherwise. So that's the agent's utility function. The classifier designer wants to predict the true label accurately. So basically, the goal is to minimize the expected error. And users' actions are given by this expression here. Users' utility is the term in the big brackets on the right-hand side. This is the outcome of the classifier F. So given a classifier F of x prime is either 0 or 1. So it's the outcome of that classifier minus the cost in misrepresenting the true label x to another true feature vector x to another feature vector x prime, right? So the manipulation is costly. Well, so the goal of, or maybe the objective of the individual agent is to manipulate the feature in order to get positive classification with least cost of manipulation, right? So that is to find a point on the classifier boundary which is least costly to represent given the true feature vector x. Well, now we have the cost. We'll consider that the cost is non-negative. Truthful reports incur 0 cost. These are standard assumptions. And the system's goal is to minimize the error or maximize accuracy that is given here. Now, this leads to, so think of this setup In applications we just discussed, maybe it's health risk prediction or bank loan approval, promotions, and so on. The goal here is to find out, maybe in bank loan approvals, the goal is to the goal is to kind of reliably identify the likelihood of individuals, default, right? So whether the person would default loan or not. And the goal of the individual applicant is to get the loan, irrespective of the applicant is planning to pay back the loan or not. So this is basically misalignment in the goals of the algorithm designer or mechanism designer and the goal of the individuals who are affected by these rules. Okay, so the gaming we consider that that happens, and then this gaming at the deployment time leads to the training error, generalization error, and so on. This problem is not new, the problem of gaming, and I will go back to I think 250 years back to a real world kind of incident in India where the British kind of wanted to have or set up a camp in Delhi, and they came up with the mechanism. So they were afraid of these snakes around the camp. These are cobras. So they wanted to kind of incentivize the local population to kind of kill the cobras, right? So, or the goal here, or the objective here was to reduce the cobra population in the wild, right? So that was the intention. They came up with the mechanism to pay individuals to kill cobra. So you get a reward if you bring a dead cobra, a certain reward, let's say $1 or something. However, this has some unintended effects or something called as perverse incentives. Since individuals were incentivized to not really reduce the cobra population, but to show that incentivized to get the money that's on offer, they started farming cobras, right? So, or maybe raising cobras in their backyard, which led to this problem of, of gaming. So the goal here is that once we have some objective function, so objective function here was to reduce the cobra population, and the proxy is to get the dead cobras, killing as many cobras as possible. That's the proxy of the true objective. However, if the model or if the algorithm does well on the proxy, it does not necessarily do well on the objective function that we care about, which in the presence of strategy, right? So, for example, individuals are incentivized to do well on the proxy, that is reduce the error or maybe show more efficiency on that. However, this does not translate into, so for example, if people start farming cobras and then killing them, it does not reduce the wild cobra population. So does not do better on the objective function itself. And that's the problem where we call strategic learning. So we look at this problem in the machine learning setup, right, with applications such as loan and college admissions and so on in mind. Yeah, so at the heart of it is this problem that your training data set and test data sets are not the same. And let's consider a very basic one-dimensional to understand this problem better. Let's say that let's look at a one-dimensional problem. So let's say that the blue kind of curve here represents negative examples. This is a realizable data. We have realizable setting with F star being the optimal classifier without any strategy. So F star attains zero error, right? So all the points to the right of F star are classified positively, to the left of F star classified negatively. Now, Now consider this in the presence of, consider the same example in the presence of strategic individuals. Suppose we implement this F star in a real world, then if the point, I mean, if the samples from in the deployment time, at the deployment time, is towards the right of F star, right? They're anyways classified positively, and they have no incentive to misrepresent their feature. Okay, so X axis here is the feature. If the sample point at deployment time is between 0 and -1, which means, and let's say that the cost is just the length of the distance from the point and F star. So the individuals are incentivized to misrepresent in a particular annulus of 0 and -1. All these individuals will misrepresent themselves by reporting feature as 0, right? Which means that they will incur a cost which is less than the utility they gain by being classified positively by F star. How can we solve this problem? Well, you move F star from 0 to 1, and then so this will result in another problem where you will have that without strategy, the individuals which are labeled positively will now be classified as negative. However, in the presence of strategy, when individuals are strategic, all the individuals between this annulus 0 and 1 will misrepresent themselves to be F star equal to 1, right? So which means that they will be classified positively, but they will face some cost. Whereas and then will have higher accuracy than the naive classifier F star, Bayes optimal classifier F star. So we want to understand this setting in higher dimensions with more complex class of classifiers and cost functions and so on. So before going to the system, I mean, in most generality, what we will do is we'll see this as kind of a game played between two agents, a system and users. So we can think of users as a collective of users instead of one agent individually. Right. So the system learns a classifier from some training data. We will assume that this training data is coming from the original distribution, D train, training distribution. The system kind of declares this F publicly, or at least F is available to the users through some means, right? So either system says that this is going to be my criteria for loan approval or admissions and so on. So this criteria is publicly available. Users will look at the criteria, and they also have access to their own features. They look at their features and the criteria, and possibly misreport at some cost their features to obtain the desired outcome from that criteria, using that criteria. Our goal is to minimize the risk under this behavior or this distribution shift resulting from strategic misreporting of the features, right? So, okay, so the objective function, you can write this objective function this way. There's one small point here. So I'm considering delta f of x is to be unique. However, it is enough that this is predictable in some sense. Okay. So given an x, individuals respond to a classifier rule f by reporting delta underscore f of x. So this is going to be the report. This is a strategic report because this is a rational response to f by an agent x. Okay. All right. So I think there's a typo here. So this c of xy should be less than or equal to 1. The agents will misreport agents would misreport their points or their features, as long as the cost of misclassification or cost of positive classification is not more than 1, right? So as long as you get positive utility, agents will misreport. Otherwise, agents report truthfully, and in that case, agents receive the utility of 0. If you can see, this is a nested min-max problem, and in general, it's kind of hard to solve. What we will do now is consider some examples of different cost functions. Notice that the whole problem depends on the cost function in very non-trivial manner. So the cost function decides or dictates what along with f what the response should be. This response basically is incorporated in the objective function itself, and hence we would hence for different cost functions, both the accuracy or the error rate, as well as the performance, as well as individuals' ability to manipulate changes, right? Okay, so we'll consider few cost functions. One simple cost function is this. We'll look at linear classifier and this kind of cost function, L2 norm. Here the idea is, if we have linear classifier, the idea is that the agents will not misreport, or maybe agents will truthfully report if they are on the right side of the boundary, or they are too far away from the other side or the wrong side of the boundary where they get negative classification, and it is not profitable for them to misreport and get positive classification. Otherwise, they will just identify the point which is smallest in terms of L2 distance on the boundary of linear classifier. So that's the strategic misrepresentation. One another interesting class of cost functions is studied in literature is the separable cost function. Okay, so for example, consider this inner product. I mean, absolute value of inner product is a positive value of the inner product between alpha and y minus x. Y is the point that is misrepresented by an x, right? So by an individual with feature vector x. Now, let's try to understand this to basically understand how the geometry of the underlying classification criteria or classification rule changes in the presence of different cost functions. So it is and then we're considering this in a product, a separable rule. So note that moving in the perpendicular direction of alpha, that is along these dotted lines, is cost free. That is because it's in a product, so it's cost free to move from x prime to x. So now if the individual with feature vector x prime wants to manipulate and get a positive classification, it's as good as individuals having feature x, right, in terms of classification cost. And let's say that y is the least costly point on the classifier boundary f of classification rule f from x, which means that y is also a least costly point from x prime or any other point on in this dotted line, right? So on the hyperplane, which means that the classification rule f and another linear classification rule f prime, which is given by the shaded slightly so shaded region f prime, that gives this similar, I mean, exactly the same error. So it changes the geometry or underlying complexity of F as well. The classification rule intricately, I mean, it's a dependence between, has a dependence on the underlying cost function as well. Okay, so now since it depends on the cost function C, now we want to understand whether learning in general, learning a classification rule is even feasible, right? So or with more number of data points, can we get closer to, or can we reduce the error of a classifier that we learn? Okay, so we will now try to, just extend the definition of VC dimension and shattering for strategic classification. Notice that what we have done here is simply consider the strategically reported points, delta H of x1 to delta H of xn, instead of considering original points x1 to xn. Okay. So, the shattering points is the number of points, or maybe how many distinct binary outcome patterns that can be induced on n points, right? So all possible labelings that can be realized by some class, possibly different for each labeling, some classifier from classifier class H. Okay, so and then unlike standard shattering coefficient, here the classifier is evaluated on manipulated features, that is delta H of x1, which depends on H also, right? So which depends on the classifier that the classifier under consideration H. So it is not straightforward if a classifier class has a VC dimension, some VC dimension, whether the same classifier class will also have same strategic VC dimension. Okay, I'm not sure. Can you? Okay, so right, so right, and now let's move to the strategic VC dimension, which is just the maximum value or the largest number of points for which the hypothesis class can realize every possible labeling. It is also the analog of VC dimension in the non-strategic setting. It kind of generalizes the VC dimension definition. As I have discussed earlier, the cost is important, and this is a very important result. If the cost is cost depends on the starting point, right? So the point which is sampled from the training data or the original point X, then if it is independent of that point, then it is called instance invariant, and in instance invariant setting, strategic VC dimension and VC dimension of the classifiers is not much different, right? So it's just additive 1 or 2. The point here is that if we make the cost function dependent on the starting point, or the point in which is basically the true feature vector, in that case, strategic VC dimension is infinite. So this kind of this kind of problem is not learnable. So this is a important result. Now we will give a learnability result for the concept class H and separable cost function. So, and this is where the separability is an important assumption. For the separable cost function, we can say that the appropriately modified expected risk minimization ERM rule is learnable. So this setting of learning in the presence of strategic agents is PAC learnable, or in the presence of strategic agents, we can learn optimal rules with sufficiently large data, with sufficiently, desirable accuracy in terms of pack sense. Okay, so this is a strategic classification. Now we will look at couple of variations of strategic classification. One of them is performative prediction. As I said earlier, strategic classification assumes that the the feature vector changes. So that is, the reported features and the original features are not the same. It's basically, the report is a strategic report. However, there is no change in the labels. The labels remain constant or untouched. In performative prediction, we also assume that the change in the cost incurred, or maybe the efforts put in to change the features, also leads to change in qualification, that is the labels. Now, there is a the joint distribution on features and labels changes. So this given a classifier with, or maybe some rule with parameter theta, the original distribution D changes to D of theta. And now we want to understand what is the predictive optimal policy. We want to learn this policy under changes that are induced on the joint distribution over labels and features by classification rule, or maybe other rule, classification rule in this case, theta. Okay, so L here is the loss function. You can think of this as expected error. Yeah, so now the deployed classifier has performative effect on the qualifications, that is the labels. So performative risk is simply this quantity, which is basically the expected value. So this R should be E. So expected value, expected loss for under this distribution, induced distribution D of theta. Okay, so and then what we will do is here in at least in this work, people considered the iterative version of this, where we change the thetas, the parameter theta over time, and analyze the stability. So stability here is a stability point is a point which do not change under the induced distribution D of theta. Right, so for that D of theta, we get back the original rule, which is which we had before making an update. Okay, so now we have two notions. One is performative stable, and the other one is performatively optimal. The question here is, when do these two rules coincide? Right, so when we have some setting, which is when the loss function is sufficiently smooth, convex, and the distributions are Lipschitz with some parameters, then we can say that performative stable points, we can learn performative stable points. This is risk minimization kind of frameworks converge to performative stable points, as well as performative stable points are close to performative optima. Okay, are very in a very small neighborhood around performatively optimal points. Okay, so now in our recent work, we tried to kind of we tried to understand the two settings in a in a slightly different way. Okay, so we were thinking of improvement aware strategic classification. So take a strategic classification setting where individuals respond to a given classifier. However, we will also add the performative component to this, right? So this is the error in terms of in the presence of strategy. So that is, we're incorporating the strategic response delta F while evaluating F on the original labels Y. We'll also call the improvement aware error as the expected error when we consider the improvement labels. So y might have improved to y prime as a result of, manipulation at cost, and this cost may be, cost for maybe paying back the loan and so on and so forth in our applications, right? So eta here is a labeling function. And the goal here, as in the goal of performatively optimal strategies, is to find an improvement aware classifier, which is optimal in terms of improvement aware error, which is given above. Okay, so and the goal here is, and we'll also assume that it is linear. Right. So let's go over some of the important results. So when we are in, let's say, a linear regime, we show that the optimal classifier with non-manipulated data, right? Which means that you just learn the linear classifier with given data without assuming that the agents are strategic at all. And this is a naive approach. Let F star be that classifier. We show that the optimal strategic classification rule is just a sort of, we just have it's just around the corner, right? So it just sort of shifted rule, which share the same weights, the feature weights, but a shifted boundary, shifted by a parameter given by W and alpha, which correspond to the optimal classifier's boundary. Okay. The more interesting part here is that the optimal improvement aware classifier, the classification rule that not only recognize the gaming or the manipulation, but also recognizes the feature improvement as a result of those manipulating agents putting effort, or maybe qualification improvements and so on. These rules are, that rule is somewhere between the optimal naive rule or Bayes optimal rule and an optimal pessimistic rule, which does not recognize the feature improvement. Okay. Not only this, the improvement error of the optimal or maybe a pessimistic rule, strategic classification rule, is less, or at most as much that of the error of the optimal naive rule, which means that without any additional information between two classification rules, which is one is naive, the other one is very pessimistic approach, it is always advantageous to deploy or implement the strategic and more pessimistic rule in practice, as long as the some of the technical constraints are satisfied. Okay, so the key takeaways here are that traditional machine learning algorithms perform poorly in strategic setting. On the other hand, overfitting to a strategic nature is leads to additional errors. When particularly when we expect individuals to kind of do better with putting efforts, and strategic classifiers are learnable under reasonable assumptions. And then there are several questions here, right? So how do individuals react to different information structure that they have? All of them may not have full access to F. There is also a problem of social burden, which is basically how much of additional effort for is in expectation is put on individuals who are already having positive labels, right? Users may be heterogeneous in many sense in how they look at the classifier, how much information they have, and their behavior and their kind of response to the information that they have, and so on. Beyond classification, there are several settings where this framework is relevant. One is ranking, clustering, bandit problems, sequential learning problems, and so on. Yeah, so now we have considered, in this talk, we have considered that individuals are manipulating the system's classification rule. There are several applications where system try to understand the user's behavior and kind of manipulate and persuade users to take desired actions. These are strategic representation settings, targeting in online platforms, persuasion, and so on. So with this, I think I will stop here. If there are any questions, please let us. I think I
Okay, thank you very
went
much.
over time. Yeah.
So time is limited. Are there any quick questions? I have one actually. So
Yeah.
what's the relation between strategic classification and performative learning?
So strategic classification and performative learning both consider that the features change, right? So the feature vectors do change in response to the deployed rule. However, performative prediction also takes into account the possible change in the labels, which strategic classification does not do.
I see. So is it a special case of performative learning?
Yes, we can say that it's a special case, but it is studied more in terms of there are several strategic classification kind of deeper studies. So if we consider performative predictions, the set of results are very limited because it's more general setting and
Mm-hmm.
so on. But yeah, it's a special setting. All the
And
results
one
from
more,
performative
yeah,
prediction will apply to
yeah,
strategic classification.
yeah. And one more question is about the iterative version. So this
Mhm.
seems to be an extremely challenging scenario, but this must
Yes.
be quite important. But
Yes.
do you have to consider any like accumulation of errors over iterations?
Um, I'm not sure what you mean by accumulation errors. It's
Because if you make one step prediction, maybe
uh-huh.
our prediction is not perfect, right? So then
Yes,
later on, you need to build upon this solution for the next
yes,
iteration. Then the error is
exactly.
accumulated over time, over iterations.
Right, right. But we're mostly interested in okay, this is a very interesting question. We're mostly interested in the final error or convergence to an equilibrium. Uh, I'm not sure of I'm not aware of the work which studies accumulation of errors.
Mm.
Um,
If you consider an online learning scenario as
right,
written
right,
here,
right.
maybe you
Regret
could
kind of
take
thing.
into account, that kind of thing naturally. But if you
Yes,
really solve exactly the problem step by step, then it seems to be
yeah,
problematic.
right. So yeah, so I think couple of works study convergence guarantees and the rate of convergence to equilibria point, but not really from regret minimizing or accumulation error, as you said. Um, yeah, I'm not aware of. Yeah, but it's a very interesting question. Yes.
Okay, thank you very much. So if there's no further question, maybe we have to stop here. So thank you very much.
Thank you.
I'm really happy to be here to share our recent progress on one-pass Bandit learning. So this is the outline of this talk. I will introduce the interactive learning and one-pass bandits, and also its implications to reinforcement learning. And finally, I will summarize a little bit. So the key message of this talk is trying to respond to the question: how should we do the online learning or interactive learning without revisiting the history while still maintaining some strong statistical guarantee. So nowadays, many machine learning systems are interactive with either environments or the users or whatever, like the recommendation system, agentic system, or self-driving car. So for an interactive learning system to be effective and efficient over the long horizon, because the time horizon can be very large, like millions or billions, or even unbounded after the deployments. So it is impossible to store all historical interactions. And clearly, using a refitting method is impossible, because like using a standard MLE maximum likelihood estimator at each round, this will be filled at scale. So that's why we want to propose the one-pass learning. So basically, we want to like in the statistical estimation scenario, we want to design an estimator with a one-pass property. If it's there exists a state st such that it enjoys a fixed size, which is irrelevant to the time t, and then we will online update this state and then discard the data item zt, and then we will transform this st as the statistical estimator ct hat, and we want to ensure that update and the computation are independent of t. So so clearly for one-pass learning, we want to ensure that the per run time or the storage memory are only scale with the polynomial time with d independent of t, and no historical data kept, especially due to some privacy issue or also the memory issue. And for the interactive learning, Bandit is a very nice abstraction. Actually, Bandit can be regarded as the simple step decision version of the reinforcement learning. If you check this very famous book written by the Sutton and Battle, they introduced the multi-Bandit just before introducing the Markov decision process. So Bandit is the single-step decision-making process without the state transition. And for the Bandit problem, among all multi-Bandit is simply the formulation. It abstracts the exploitation and exploration trade-off using a very simple model. Imagine that you have 4 slot machines in front of you, and you're trying to pull one of them and to maximize the reward. So you have to make the decision and to balance the exploration and the exploitation. And for the linear Bandit setting, this is even more important for the machine learning community, because for machine learning, we usually have some feature information. Like in the book recommendation, we have some slide information to characterize this book. So each arm is associated with the feature vector x, and the reward is parameterized by this x and also an unknown parameter theta star, and subject to some random noise eta t. And for the linear Bandit is very important for RL and more general even like machine learning. So consider these 2 papers that are from like 6 years ago from the Bandit community. They initiate the study of the theoretical study understanding of the functional approximation, which is a very successful techniques in the RL practice. And let's go back to the linear bandits. How to solve this problem? So a very successful and a very nice algorithm is called CB. So basically, it conducts the estimation and the action. So it will start with the loop. So this is the PDF, so I cannot use the animation. But basically, you can start with the this learning history, and you have T round learning history, and then you use this input and output pairs and trying to estimate the city head. And then based on this city head, you can construct a quantity called the upper confidence bound. Upper confidence bound is trying to ensure that this quantity is larger than the expected reward. And then the arm selection is very simple, just maximize the upper confidence bound this quantity. And you got this arm, this action, and observe the corresponding reward, and concave these new pairs into the learning history and trying to do this loop again and again. So there are 2 important parts in the algorithm design. One is this parameter estimation. For this parameter estimation, a natural idea is trying to use the ridge regression because here is the linear regression problem is trying to use the ridge regression to estimate this theta star, and you got this theta t hat. And another important part is this action criteria. As I mentioned, we will use the upper confidence bound. So basically, it consists of the two parts. The first part is trying to use this theta t hat, this estimation, and inner product with this xt transpose theta t hat, and this is the estimation of the expected reward. So this is the exploitation because you use the historical information trying to give the estimation and then got this value. And then in addition to this exploitation, you will have certain amount of exploration, which is in the form of certain local norm in terms of this VT. V is the covariance matrix of this ridge regression. So this is the mean structure of this algorithm. And this algorithm have very nice theoretical guarantee because it can enjoy near optimal regret. And if we see the linear bandits, we can see that this problem solving is very easy because it admits quadratic loss. So linear UCB is naturally one pass because as long as you can maintain this sufficient statistics, this covariance matrix VT and this BT vector, and you can do the online updates, and even better, you can explore the rank 1 structure and trying to give this rank 1 updates. So you can see that we don't need to keep the historical information. We just maintain a state in terms of this VT and BT, and then we can update our estimator CT hat incrementally. So clearly this is the very special structure due to the quadratic laws because this is all these updates are due to the analytical closed form of the solving this ridge regression. But linear bandits is always very simple to solve, and to enhance its expressivity, people are trying to generalize to the more broader setting. Like the generalized linear bandits is it conducts a very minor variation, just introduce the mu function, which is the nonlinear link function here. And also, people trying to relax the assumption in the standard linear band is that the noise is sub-Gaussian noise. Here, we will allow that this noise is the heavy tail noise, which means that on the very extreme large, this noise, the probability mass is still reasonably large. So I will introduce these two models in more detail. So generalized linear band is trying to give the generalized linear reward modeling, and in this form. And clearly, a standard linear band is a special case with the identical mapping. And more importantly, it can capture some logistic model. Logistic model is a very important model in the computer science, or even beyond the computer science in the engineering. Because it can usually used to model binary feedback like click or not click, prefer or not prefer, using this logistic modeling. So trying to solve this generalized linear bandits problem invents some method using the UCB criteria. So again, it is the estimation and action loop. So for the estimator is use the regularized MLE estimator. And here, the loss is no longer a quadratic loss. It is using some log likelihood function over the generalized linear model. So if we check the special case of the logistic model, you can see that this is clearly not quadratic, though it is convex. Okay, for the action is basically the same. You can use this estimation estimator and to give the an estimation of the expected reward and then add a confidence bonus using the covariance matrix. Okay, so this is the pipeline of the generalized linear bandits. So similarly, for the heavy-tail linear bandits, again, we want to relax this eta t from sub-Gaussian to heavy-tail. So heavy-tail only ensures that a low-order moment is bounded. So even its variance can be very unstable. And on contrast, the sub-Gaussian noise is very have a better properties. It ensures the exponential tail decay. So all the moments of this random variable are controlled. So to solve half-tail linear bandits, there are a bunch of methods, but recently there are very nice paper and give a very elegant algorithm using this adaptive Hoover regression. So Hoover regression is the very classic technique to in the robust statistics, trying to reduce the penalty for large deviation. So they will set a threshold tau, and after this tau, it will be a linear, and inside this tau range is still the quadratic. So clearly, this estimator, this loss is no longer entirely quadratic. It's only partially quadratic. So for these two problems, if we put them together with the standard stochastic linear bandits, we will see that previously we have a one-pass update because of this quadratic loss. But currently, we only have some convex loss function instead of the quadratic loss. So how to solve this minimize or this Acme problem? You have to solve that repeatedly. Like at run t, the computational cost is like order of t times log t using some strong convexity of this objective function. And also you have to store all the historical data trying to make this function expression kept in the memory. So clearly this is feasible for a lifelong scenario. So the natural question is, can we generate? Can we solve this generalized linear bandits or habitual linear bandits problem with the one-pass algorithm? Okay, so clearly a very natural idea is trying to use the stochastic gradient descent to incrementally solve this MLE. Like you use the newly coming data and trying to do the gradient descent. But why this stochastic gradient is not enough or is even infeasible as far as I know? Because the SGD is the typical optimization method, and its error is typically characterized in the form of the Euclidean norm. But for the bandits, we usually need some estimation in a self-normalized covariance matrix exploration, which means that we usually need have some exploration optimization error trying to capture it in some VT norm so that we can have a VT type exploration. And the second part is even more severe because for the Bandit setting, as I mentioned, Bandit is a very a good test bed for the RL. And for the RL, there is the on-policy issue. On-policy issue means that the decision is based on the estimation, and estimation is also from the historical data, which is related to the decision and the action. So clearly this process is no longer an IID process. So classic guarantees, especially for the stochastic gradient analysis, are not applied here. So our method is use a very classic method called the online mirror descent, which is the very important, powerful framework for the online regret optimization. So the main takeaway of this OMD method is it considers both gradient update and the geometry. So this geometry is characterized by this Bregman divergence. If you take the different psi, you got different Bregman divergence. Like you can use the standard L2 distance, or use the this local norm in terms of this A matrix, or use some even negative entropy. So this is very important because for online learning, many online algorithms can all be covered by online mirror descent. So this is the standard. But how to apply this OMD OMD optimization method to our case? The key idea is trying to encode some local norm, which is required to be curvature aware. So basically, we will use some local norm. So the psi, this mapping, is typically choose as this kind of way, XHT norm square. Then the OMD update becomes this in this form. So basically, it did a gradient descent, but it's sketched by some geometric matrix. And this geometric matrix is curvature aware, because this will use some weighted rank 1 increment to keep as a state, like here. And so if we can do this correctly, and clearly this computational issue is very won't be a bother, because we can use it's clearly independent of t, and explore this rank 1 updates. The time per run is d squared, and memory is also d squared. It's all independent of t. And but here is the important thing is this matrix, this curvature aware matrix, especially this weight, requires some careful design. For the generalized linear bandits, you have to explore some self-concordant property to do this geometric matrix. And for the heavy tail bandit setting, you will need to use some adaptive design of the threshold function to adjust this region. Okay, so here I will give a very brief sketch of the analysis. So basically, for this kind of online mirror descent analysis, we will have this kind of inequality. This is the very simple twist of the classic regret analysis of the online mirror descent. But here, you will show that here is the ct plus 1 minus theta star. This is the estimation error. And importantly, we have incorporated this curvature information ht in this local norm. And then if you can properly choose this local norm ht and also the surrogate loss, this gt, you can do this estimation error analysis very smoothly. And importantly, this kind of analysis framework is compatible with the self-normalized concentration. I won't expand the details here, but this is the some key technical tools to address the on-policy dependency. Remember that in the bandits and RL scenario, the xt and ct, this estimation and action, they are dependent for each other. And this analysis framework is compatible with to addressing this on-policy issue. So for generalized linear bandits, again, we will design this ht using some self-concordant property and also this second order approximation using some look-ahead regularizer. I won't expand the details, but here, this final function ht will like this kind of thing. And using this kind of curvature-aware local norm design, you can ensure that this estimation error in terms of this ht is very good in terms of the it's in the order of the root d log t. And with this kind of estimation error, you can get a very nice final regret guarantee. So this is the first one-pass generalized linear bandits algorithm with almost optimal regret guarantee. And this is published in last year NIRPS. This is the joint work with Professor Sugiyama. And for the heavy tail bandits, this is very similar. You will use some, you have to explore the locally quadratic property of this Huber loss, and trying to adaptively adjust this threshold and renormalize the factor in this Huber loss to explore this curvature. And you can also give a very nice exploration estimation error, and also give this almost the optimal regret. Importantly, this regret can be even related to the new. This is the problem dependent regrets. This new is the some statistic measuring the amount of the heavy tail noise. And this is published last year ICML. And I'll very briefly mention about the RL implications because of short of time. So basically, the first application is the understanding the functional approximation. Functional approximation is one of the most important successful techniques in the empirical RL. And trying to understand the functional approximation, people usually start from the linear functional approximation. So the reason to make this linear and DP parametrization, because it can be reduced and solved by the linear bandits, and the technique for the linear bandits is very mutual. So people trying to use this kind of modeling, but people always blame that linearity is satisfying in practice. So people start to consider some general functional approximation, but this is very in the complexity language, so it's computationally inefficient. So our question is trying to answer our result is trying to answer this question. Can we give some computational efficient algorithm beyond the linear function approximation? And there is the very nice modeling function is the monomial logistic function. It will introduce the softmax after softmax function to perform over the induced probability. So that this is the modeling. You can see that there is basically a linear parameterization, but after this linear parameterization, there will be a softmax function. This is just like the neural network. The last layer you have a softmax activation. And so I won't expand details, but you know basically using this MNL mixture MDP, you will have a broader modeling capability, but there are also another challenge this arise due to this nonlinearity, and I think you can shockingly feeling that this MNL MDP this modeling is very related to the logistic activation function. So we can deploy our new method for the logistic bandits or the more broadly generalized linear bandits problem for this problem to give a one-pass estimation. And for this work, we give the first for the first time to give a matching result for MNL mixture MDP, which is nearly optimal, and except for the dependency on this edge. This is the nerve seen 2 years ago. And the second implication is about RLHF. Nowadays, RLHF is everyone knows about RLHF is this the preference optimization trying to align the model towards the human preference. And for this problem, a standard pipeline is the reward modeling and the PPO. And for the reward modeling part, you're trying to use the pairwise preference data and trying to learn some reward model. And you know, sometimes people want to do the online RLHF, especially after the model deployment. People collect more and more data, and especially about the preference data, and they want to update their model timely. And in this scenario, you will suffer a critical issue about the reward modeling, because in the reward modeling you have to make these updates like sometimes. So if you do a typical reward modeling, you will use this Bradley and Terry model and trying to use the maximum likelihood estimator to give this reward model. And in the online scenario, at the updates iterate t, then you have to store all the historical data and also calculate this MLE estimator using some convex optimization technique. And this will be very time suffering. And here we do some simplified results using the linear reward model assumption and with this BT model. And then we can reduce this problem as the contextual dueling bandits with the logistic activation. In this way, you can imagine that we can using our technique to and get estimation error and regret guarantee for RLHF. And surprisingly, this kind of way can also have some empirical gains in real-world applications, in real-world data sets. This is in the last year NERPS paper. And to summarize today's talk, I try to we try to answer one question is how should we do the online interactive learning without revisiting the history, and importantly we want to maintain the strong statistical and regret guarantee. So our test bed is the one-pass bandits. This is a very important and fundamental question in the machine learning and online learning community. And we will see that beyond linear bandits problem, without the quadratic loss, everything becomes very challenging. And our proposal is the use linear descent estimator and trying to use this optimization technique as the statistical estimator, in which the curvature-aware adaptivity is very important, especially in the local norm design. So in the spirit, you can kind of think this is like from the SGD to the ADA grid or the ADAM. The curvature-aware adaptivity is also important to make all those optimization techniques apply in the real world applications. And we also discussed about very preliminary implications to the RL, and we are still exploring more and more scenarios. So this is the reference of this talk, and thanks for all the wonderful collaborators. And that's all for my talk. Thanks.
Okay, thank you very much. Are there any questions? So let me start. So from the previous talk, so we had strategic classification, so where current prediction affects the next input X. But is
Yeah.
that framework included in this online learning scenario?
Okay, this is very nice question. Is indeed related. I think on-policy issue is also one of the source of the strategic prediction, I guess, or called the performative prediction. So it's like this on-policy issue is one source of or one of the reasons to make the performative prediction happen. But perhaps I think in the performative prediction, you will also introduce some external like non-stationarity or something distribution shift to other reasons. Yeah, like in the multi-agent system. Yeah, their environment is very complicated. Yeah, but here I only focus on policy issue.
But there seems to be a possibility to like merge these two ideas into the same framework.
Yeah, it's a very interesting question trying to combine these two things. But I don't really know how to like to decouple this on-policy issue dependency and some external source of the non-stationarity. But if this can be possible, I think yeah, this combination with some guarantees will be also very interesting to explore.
Yeah, thank you. So then, okay, we have three questions in the chat window. So can you read it?
I saw the three questions in the chat room. For the first question, I think this is a very technical question because why we need this self-normalized exploration is because in most of time we need to make this exploration in a very non-uniform way. Otherwise, if you explore in a very uniform way, this regret cannot be controlled. This is the technical reason. And the second one, so the second question is, yeah, this question. So first, there are two parts. First part is this XT transpose. This already incorporates certain of the curvature information, and more importantly is this alpha t. This design of this alpha t is very important. Like in this generalized linear bandits, you will see that this alpha t will relate it to the Hessian of this in current point. So this is related to the curvature. And in the heavy tail linear bandits, you will see that this alpha t is related to the threshold function in the Huber regression. And this threshold determines whether it is quadratic or the linear function. So this is related to the curvature. Yeah. So for the third problem, kind of because for the RLHF, we also need to do some experiments. Yeah, it's more efficient than the vanilla algorithm using repeated MLE estimation. Yeah, but more exploration are certainly required.
Okay, thank you very much.